Dear students, welcome all of you to 15 Minit Xikhya and especially to the first lecture in physics on this platform. You are all students of undergraduate courses with physics as a subject in different colleges and universities of Assam and the Northeast. I hope many of you will stick to physics, will choose physics as a career and will become good scientists in future. But many of you will certainly leave physics after completing the course to choose some other career path. It does not matter whatever you do, wherever you be, it will be always an added advantage for all of you that once you were students of physics. I congratulate all of you for choosing physics as a part of your career. In this lecture, Physics from Newton to present days, I will give you a brief overview of the subject matter of physics, why do you study physics, and how physics has evolved from the time of Newton to the present days. Subject matter of physics is really vast. Physics is concerned with almost all the phenomena that we observe in nature. Their explanation on the basis of certain conceivable physical principles without invoking any supernatural agents. Here, I am just showing a few of them. A physicist tries to explain the structure of matter at the minutest level, at the quark level, to the largest structure in the universe, the formation of galaxies and the construction of the universe as a whole. It tries to explain how energy is generated inside the sun, inside the stars, and how a similar process can be recreated on the surface of the earth for the benefit of mankind. It is also concerned how a virus can be crystallized. Almost all the technology that we enjoy in the today's world, from the semiconductor revolution to the internet, World Wide Web, all of them had their origins in the physics lab. Not only that, physics is also concerned with some fundamental issues, some fundamental questions. One of the most fundamental question is where from we have got the matter, what is the origin of mass in this universe, mass in our body. Everybody remembers the great sensation when the so-called God particle was detected a few years back. Another most interesting question, or a question that has been asked by man from antiquity, is about the origin of our universe. In earlier times, we believed that the universe exists from infinite past to the infinite future. But in today's world, with tremendous improvement in the theoretical understanding of our universe, we now believe that we had a finite beginning in the past. There was a day without yesterday when the universe along with the time was created. Above all these, certain questions which were earlier addressed only by philosophers, like why are we here? This kind of question is also now being addressed by physicists. Now I am going to discuss the different disciplines of physics that evolved from the time of Newton to the present days. I'd like to consider physics as a big tree with two big branches. The branch that developed before 1900, that branch we call as the branch of classical physics. The branch that developed after 1900 from the beginning of the 20th century, that branch of physics we call as the modern physics. Under the classical side, we have this most important branch, classical mechanics, about which I will come a bit later. Thermodynamics is the branch where we deal with the relationship between heat, energy, and work. Electromagnetism, the study of electric and magnetic properties of matter. Optics, study of light. Coming to the modern side, the most important branch is the quantum mechanics, the world of microscopic particle. Relativity, which is synonymous with the name of Einstein. Nuclear physics, which was born along with the discovery of the atomic nucleus. Particle physics, plasma physics, biophysics, atomic and molecular, cosmology, condensed matter physics, and in fact, many other branches can be added on the modern physics sides. It will not be possible for me to discuss all the different branches. I'll just pick up two, one from the classical side and the other from the modern side. So in these lectures, from the classical side, I'll discuss about the classical mechanics, and from the modern side, I'll discuss about quantum mechanics and see how the concept evolves from the time of Newton to the time of quantum mechanics or to the time of 20th century. Classical mechanics is the oldest branch of physics. The name is synonymous with the name of Newton, and it can be said that it was born along with the publication of Principia by Newton in 1685. I'll just mention some of the salient features of classical mechanics. The Newton's three laws of motions, Hamilton and Lagrange's equations, and the law of universal gravitation. These are the pillars of classical mechanics. And their structure of classical mechanics stands on this law. It deals with the motion of bodies under the action of force. When we apply force on a body, how the body moves, what will be the trajectory, etc. are the questions that are answered in classical mechanics. This set of laws are applicable to the so-called large bodies. They are not applicable to the world of microscopic particles like atoms and molecules. The Newton law of gravitation is considered to be the first unification of forces. Before the time of Newton, people believed that there is one set of laws for the earthly beings, for the bodies on the surface of the earth, and another set of laws for the heavenly bodies that hover in the skies, in which God lived. But Newton showed that it is the same law that determines the fall of an apple to the ground and the motion of the moon round the earth. This was considered as a great moment because the quest of unification is an universal quest of all scientists, and this can be considered as the first unification. Classical mechanics not only explained the world beautifully, but it could even predict something new. It predicted the existence of Neptune before it was discovered. But the most important feature of classical mechanics is its deterministic nature. Classical mechanics is deterministic. Deterministic in the sense that by solving the equations, you can exactly predict what will happen in future to a particle or to a body. This very feature separates it completely conceptually from the world of microscopic particles. The belief of the scientists in the determinist nature of classical mechanics was so much at the time that the great mathematician Lagrange once said, "Give me the information about all the forces acting on you. I can exactly predict in which particular restaurants you will dine, with whom, after 20 years." This statement actually expresses the deep confidence of all the scientists in the deterministic nature of classical physics. Now I am coming to the modern physics side. Quantum mechanics, the very name implies that it is the mechanics of the macroscopic world. It is the mechanics of the world of electrons, protons, neutrons, etc. It brought a complete revolutionary change in the way we understand our world. Till the beginning of the 20th century, people were very content, very satisfied with the description of the world with the help of classical mechanics. But in the second half of the 19th century, many experimental facts came to light which could not be explained by classical mechanics. One of those phenomena is the so-called black-body radiation spectrum. You must be very familiar with this problem. Assuming light to be a wave, assuming light to be continuous, nobody could explain the nature of the graph. Another important problem that featured in the second half of the 19th century is the so-called photoelectric effect. When light of particular frequencies are incident on some metallic surfaces, then electrons are spontaneously emitted from those surfaces. All the features of this photoelectric effect could not be explained on the basis of classical physics considering light to be a wave. This is the picture of another problem, the spectra of elements. When elements are heated, hydrogen, helium, lithium, etc., they are heated, they emit light of only certain frequencies, certain wavelength. And the wavelengths are different for different elements. This feature of the spectra of elements also could not be explained on the basis of classical physics at that time. All those problems, together with some others, so created a real headache for all the scientists at that time. People were so much enamored by the success of the classical physics, Newtonian physics, that nobody dared to come out of the box. Then, at the beginning of the 20th century, the great German physicist Max Planck came up with a revolutionary idea to rescue the situation. It was actually so much revolutionary that he himself did not believe it. He just said that it was a mathematical trick to solve the problem. What was the revolutionary idea? He said that nature at the fundamental level does not obey classical laws. Even though classical laws are extremely successful in explaining all other phenomena we observe in nature till then, in this kind of situations, classical mechanics fails. We have to invent some new laws of nature to describe those phenomena. This shows the very basis of quantum mechanics, but this quantum physics that was described by Max Planck, it is called the old quantum theory. Quantum mechanics is somewhat different. I'm not going to discuss about the quantum mechanics. I'll just discuss only one very important feature of quantum mechanics, the nature of its probabilistic nature of quantum mechanics. One of the most important characteristics of quantum mechanics is its probabilistic nature. In quantum mechanics, we cannot certainly say that a particular event will occur. We can only say about its probability. So what is the probability of occurrence of a particular event? For example, consider this radioactive atom. We cannot certainly say when this atom will emit a particle. It can emit this very moment or it may not emit for the next 100 or 200 years. Consider this famous thought experiments invented by Arjen Schrödinger to expose the ambiguity of the quantum world. I am not going to explain the entire experiments, but just the consequences of it. Here is a cat in a box. There is a cyanide poison in a vial, and here is another radioactive atom. If the radioactive atom emits a particle, then the vial of cyanide will be open and the cat will be dead. If it does not emit, then it will not be open and the cat will remain alive. Now, if you ask a person who believes only in the certainty of the classical world, then he will say that the cat is either in an alive state or in a dead state. But if you ask the same question to a person who gives you answer quantum mechanically, then the person will say that no, the cat can be in a position of superposition of both dead and alive. At the same time, the cat is dead as well as alive. This very probabilistic nature of quantum mechanics was at the heart of many important debates between the giants, which are now integral part of the history of quantum mechanics. Einstein was very sad about this particular nature of quantum mechanics, and that's why he once said that God does not play dice. He did not believe on this interpretation till his death. But the important thing is that whatever may be the interpretation of quantum mechanics always works. It works wonderfully. Here I am giving a quick summary of what I have said. In classical physics, energy can be emitted or absorbed by a body continuously. There is no restriction. But energy in the quantum world is discrete. A body can emit or absorb energy only in integral multiples of a discrete amount. Classical physics is deterministic in nature. We can predict the future exactly provided we know the present. In contrast, quantum world is inherently probabilistic in nature. Nothing can be said with certainty. We can only predict the probability of occurrence of an event. This much for the part 1 of the lecture. In the part 2 of my lectures, I will come up with some very interesting problem of modern physics, particularly of the particle world. Till then, goodbye and thank you all for listening.